I'm going to open up the, uh, the slides here. I hope you had a good Thanksgiving. We're going to continue on radar here. And I'm going to go fairly fast here. Since this is an audio recording, you should be able to, stop it if you need to. Um, and go back. So we're going to go through this, and I'm going to probably do a second recording where we're going to start with thunderstorms. So we need to get into that as well. But I do hope you had a nice Thanksgiving. This will run about 25 minutes here, and then I'll have a second recording where we'll start with thunderstorms, and we'll finish that up on Tuesday. So back to weather radar, and this is something I actually stole from the National Weather Service in Hanford, Washington, a basic thing on radar for advanced spotter courses they do, and I've added some stuff into this. And we started talking about radar in our last class, and we'll continue with it. Weather radar really has changed meteorology because we can see where rain is falling. We can tell how heavy the rain is. Doppler radars, they can tell if the precip is coming toward or away from the radar. We send out a pulse. We know the frequency of that pulse. We'll get energy reflected back. But if the frequency that comes back is slightly higher, that means the the image or the rain is moving toward the radar. If the pulse that comes back has a slightly lower frequency than we sent out, that means it's moving away from us. That's the Doppler effect. You've heard it with sound. As a siren approaches you, the pitch goes up and then goes as it goes by. That same thing happens with electromagnetic radiation. It's used very heavily, by the way, in astronomy as well. It's how we can tell a lot about stars. So we can track storms, fronts. We see all kinds of things on radar, including tracking birds migrating. So it's really an essential tool for meteorologists to do, especially what we call nowcasting, which is a forecast out about 2 or 3 hours in advance. So this is a weather radar screen showing precipitation and, the very light bounce back, very low energy bounce back would be very light precipitation. And we talked about using DBZ, which is a scale that basically uses logarithms because the amount of energy that comes back from a radar pulse varies from a millionth of a watt up to maybe a tenth of a thousandth of a watt. So there's such a huge scale that if we use a logarithm, we can basically go down between 0 and 100. And that's what we're doing here. And we don't even go above 100, really. About 65 dBz is about as much as you would see. That would be hail. So what is radar? It stands for radio detection and ranging. The radar emits a pulse of radiation. It usually is in the microwave part of the spectrum. Your microwave oven in your apartment or your house is basically about the same frequency. It's about 5 to 10 centimeters if you go wavelength. And we send out a pulse. The radar spends most of its time listening. It sends out a pulse, and some of that energy gets knocked back. Radars tend to use, for weather, we use 5 to 10 centimeters because those tend to reflect best off raindrops. And of course, the energy going out from the radar is going at the speed of light, so we time how long it takes to get a reflection back, and that can tell us how far away it is. And the amount of the return can tell us a lot, not just the intensity of precipitation, but as you'll see, we can see all kinds of things. So a radar beam, the energy goes out at about 186,282 miles per second in a vacuum. It's a little bit less in the atmosphere with air, but it doesn't really matter much, although that is the exact speed is usually basically programmed into the radar. So what we get back tells us a lot about the nature of the object. Big objects, for instance, large raindrops, you get a big return. Small objects, not much of a return. And other objects, it just depends. And the amount of energy that gets scattered back to the radar depends on the sixth power of the diameter to the sixth power. So a slight increase in the size of the object that the radar beam hits means we get much more power back. So big raindrops, hail, especially hail coated with water or snowflakes coated with water, boy, they really send back a large signal. So again, reflectivity is just a fancy name for the amount of radar signal that's returned. We use decibels, which is a logarithmic scale. And so that's why you see dBz. And again, the reason we do this is we could put watts, but you would go from 1 to a million. And we don't want a scale that goes from 1 to a million or 0.00001 to 0.0001. You know what I'm saying? You want a scale that's easy to deal with. And they also do the same thing, by the way, with earthquakes. You wonder, a magnitude 6 earthquake and then a magnitude 7 is about 10 times stronger. They're using the logarithmic scale there as well. So most of the radar imagery you see, it looks the same. Sometimes the colors will be different. This one is using pink for low levels, light rain, and then green and yellow for heavier amounts of precipitation. But again, where you're not seeing anything there, the black or dark brown in this image is no reflection back at all. Yellow is heavy rain, so you don't want to ride through that. If you're on a bike or going outside, you're going to have some heavier stuff. Radar beams, by the way, out west especially, are blocked by mountains. You can see that happening on this radar. Notice the hard edge here on the left side of that radar image. Radars out west have real issues with mountains. Here in the east, it's not as bad. We don't have high enough mountains that cause a problem. And also remember that as the radar beam goes away from the radar, it gets higher and higher. Usually we tilt up at about a half a degree, but it's getting higher above the ground because the Earth is round and that radar beam is going in a straight line. A radar beam about 300 miles away from the radar is about 60,000 feet above the ground. Even if you're pointing at the beginning, if you're pointing the radar beam just right at or maybe a hair above the ground at a half a degree, if you're looking at a storm 300 miles away, you're not going to see it unless it's over 60,000 feet tall. The radar beam is that high by the time you get that far out. This is an example of heavy rain around the Seattle area. And again, you can see some holes in there, and those are due to mountains blocking the signal. Here's another view of precip on the coast, and a coastal radar, again, it doesn't see over the mountains very well. So mountains do make a big difference. So most radars we now have are Doppler radars. They not only send out a signal, but we can also look at the frequency of what's coming back. And that tells us whether something's coming toward or away from the radar. We cannot tell, by the way, if it's going left to right. Imagine you're looking at a storm 100 miles away. If it was moving 100 miles to the left, you wouldn't see any signal. We can only tell toward and away from the radar, but that's enough for us to get a lot of good information. It's basically the same thing that police use. They tend to use lasers now because they're a bit more accurate than the old style radar guns. The guns were not really big enough to give you an accurate signal beyond about 100 meters. So they now use lasers. Many attorneys took these to court in the older days before they went to lasers and won the cases, saying, you can't tell for sure that you weren't getting another car if it's more than 100 meters away. But the lasers are much more accurate now. You get caught one of those and they're pretty much, they got you. Now, again, we talked about the Doppler effect. You can watch this video here if you want. It goes more into it, but I'll move on. Now, the other thing you should know about the way we do radar now. In the old days, when I was young and studying meteorology in the late 70s, the radars, basically we kept them on the same low level tilt all the time, about a half a degree, maybe 1 degree. But we're missing out a lot of information doing that. So the modern NEXRAD radars that the Weather Service uses around the country, they do a scanning sequence, okay? And it starts off with the tilt at a half degree and then say 0.9, then 1.2, 1.8, and goes all the way up to maybe 15 degrees, and then it comes back down and does it again. The good thing about this is we get a whole picture of the atmosphere. And if you're using Doppler data, we can measure winds way up there. If there's clouds that reflect radar beam back, we can get an idea of what the wind is doing. Simple trigonometry. The negative with doing this is that it might be 5 or 6 minutes before we take another look down low again. And if we're tracking, say, a tornadic circulation or something, that's a bit long. We now have different scanning modes that we can use. In severe weather, we have a scanning mode that will go up and take a look at higher elevations, but not as high, and it will go back down and take a low-level sweep maybe every 3 minutes, and then go back up and do some more scans. So we don't go 8 or 9 minutes between a low-level scan. That's important now. But we call this a volume scan. So this is what it would look like if you could see the radar beam in each level going up, and you're getting a whole cone here. Right near the radar, there's nothing. The radar can't see really close. We call that the cone of silence, and that's what the middle of that cone is. There's nothing in there. But that only goes out a couple of miles from the radar. We can start to see precip beyond 2 or 3 miles, but not that close to the radar. So In the old style radars you see in movies and stuff, you see this kind of thing. This is what we call a PPI, a planned position indicator, where you would see the sweep going around. And you can, at work on my machines, I can see our low level sweep come in and I see the sweep going around. We don't tend to show that on television much anymore, but now you just see an image like this and you don't see the sweep going around. But it is really going around there for sure. There's a great book, A Radar History of World War II. It gets a little technical here, but it's a fun thing to read about how, and I talked about it in class, about how radars were first used, by the British looking out over the English Channel to track the German Luftwaffe raids during the bombing of London during the Blitz, and they would notice that rain would pretty much cover the radar scope, so they knew they could see rain even back then. But then after the war, the old military radars were turned into a WSR 57, and I remember those still being used back in the late 70s, and then they upgraded, and then we went to the WSR, Weather Service Radars, WSR 1988D for Doppler. So meteorologists call it an 88D, and it's a Doppler radar. They've been upgraded several times and then added dual pole as well. Hurricanes, this is a picture of Hurricane Carla. I told you the story, I think, of the reporter from KHOU in Houston who saw this on radar at the Galveston Weather Office and said, I want to put this on TV. And they said, oh, we can't do that. It'll scare people. And he finally got permission to do it and got him noticed by the network. And his name was Dan Rather. And 2 years later, as a matter of fact, he was in Dealey Plaza as a CBS reporter when President Kennedy's motorcade went through, and then ended up becoming the basically main anchor on the CBS Evening News after Walter Cronkite. And so his whole career started by putting that image on television. So that's what the old radars looked like, the WSR 57s. And they were pretty good radar. And then they upgraded them a bit more. But boy, those when I was young, that was technology, and it was getting pretty old by then. So, but they didn't have any Doppler capability at all. And those days before the internet, you had to have one person at the radar kind of doing a drawing of what he was seeing and faxing that out. So it really wasn't very good. And then NexRad came in and everything changed. We could see the winds, we could see wind shifts, we could see cold fronts due to the Doppler data. We could see rotations of rain around a tornado. We're going to talk more about that, and I'm going to show you more Doppler radar images when we talk about severe weather, by the way. We're going to have a separate section where I'm going to show you some more Doppler radar images. So I'm going to skip some of that right now, but I just let you know we are going to show you that. You're going to know before you get out of this course what a tornado looks like on radar. No doubt about that. So in the 80s, the Weather Service started putting the 88Ds out. I believe it was about 91, 92 before they were really going up everywhere. This is what the rate reflectivity looks like on the left here. This is a Moore, Oklahoma tornado, by the way. This was a deadly tornado in 1999, killed, I think, 47 people. But if you look on the right, that's the velocity, the Doppler data. And the green is toward the radar, which is on the right there where that big black hole is. And red is wind going away. And if you look just north of Moore, you'll see a bright green toward the radar right next to bright red going away. And that's the circulation there. I'm going to pop out of this slide here just to show you here. This is green going toward the radar, which is right here, and the red is away. And if you have a circulation, really strong circulation right here, that's what you would see. You'd see winds going away and winds going toward right next to each other. So that's what we can see on a Doppler radar. We can actually see the circulation around a tornado. Pretty cool, huh? Yeah, and that's one of the reasons. When they first put these up, we thought, well, we might see a tornado out 50 miles, but then the radar beam would be too high. Turns out tornado circulations go up thousands of feet. And we can actually sometimes see tornadic circulations over 100 miles away on radar. So here's the radar data, or these are all the stations. We have one in Dover. There's one at Sterling, Virginia, Wakefield, Fort Dix, New Jersey. And the radars in the east are pretty close together. We have a lot of severe weather in the east, hurricanes on the Gulf Coast and the East Coast. Not as many radars out west. One, there's not as many people, not as many big cities. Also, you've got mountains out there, so the radars don't do as well. But you can see quite a few there down on the coast. Now let's talk about dual pole radar. And this is interesting. What what most radars do is they send out a horizontal signal, like the one you see on the left. But we can also send out a vertical pulse. We can polarize the radar to send out a pulse that goes up and down instead of left and right. So why do that? Well, there's a really good reason for it, because I want you to think about a raindrop. And raindrops, when they fall, they look like inverted hamburger buns. And if you think of it that way, and I want to pop out and use my mouse again here, say here's a raindrop falling. The horizontal pulse is going to go through a big chunk of that raindrop. The vertical pulse is just going to go through a slice of it. It's a big difference. So if you look at the reflectivity from the horizontal polarized signal and the vertically polarized signal, there's going to be a big difference. If there's a big raindrop that looks like an inverted hamburger bun, the horizontal is going to get back a lot more energy than the vertical. And so you'll have a big difference in the reflectivity. We call this differential reflectivity. If it's a big round hail stone falling, look at that. It's going to be about the same. It's going to come back and you're going to get almost zero differential reflectivity. In other words, the difference between the horizontal and the vertical is going to be pretty much nil, zero. But if it's big, heavy raindrops, you're going to have a big difference in the reflectivity coming back between the horizontal. And on this screen on the right, big difference is red. And basically no difference is gray or blue. And notice this hailstone here, and then look at this circle right there. Huge baseball-sized hail was falling right there. And you notice there's big raindrops all around it. That was showing up bright red. There's a big difference in reflectivity. That's these hamburger buns falling. But where the spherical hail was, it's gray and blue. So dual pole radar allows us to actually see what objects are falling. Hail, for instance, versus big, heavy raindrops. Really, really helpful. There's another thing we can look at, and this gets a little bit into the math. It's called the correlation coefficient. That's the CC here. Here's differential reflectivity, and Z is just the reflectivity you're used to seeing on radar. You know, how heavy is it raining? And this would be light rain, heavy rain, and extremely heavy rain. But correlation coefficient is something we can get off Doppler radar. It basically says this: how correlated is everything in the radar beam? In other words, is it all a bunch of little raindrops? Is it all a bunch of inverted big hamburger buns falling? And that would be a correlation coefficient that means that everything's correlated. It would be bright red on the radar scope. That means, yeah, it's all correlated. We're all seeing the same thing. But what if you were seeing the debris from a tornado that hit an apartment complex that threw bricks and stones and pieces of wood and people and cows in the air? Then there would be a huge difference of things in the radar beam. It would not be correlated. And the correlation coefficient would be very low. It turns out, and I will show you when we get to severe weather, that the correlation coefficient is really good at telling us if a tornado is on the ground and throwing debris in the air. The correlation coefficient will drop down. You'll have a hole of blue right there in the middle of a storm. Now, this isn't showing you a tornado on the correlation coefficient, but I will show it to you later on. But I want you to understand that dual pole radar, one, tells us the size, how big, the shape of objects, whether or not there's a tornado throwing debris in the air. Dual polarimetric radar, along with the Doppler ability, gives us amazing capabilities now that we did not have before. So it really has changed a lot of people's lives, because we've been able to give really good tornado warnings that used to be very short. Now we can say there's a large tornado on the ground, maybe in a rural area headed for a town, and we know it's on the ground because we have a debris signature on the correlation coefficient. So tornado warnings are much better than they used to be. One other, and we're almost done here, one other cool thing is when snowflakes fall and they start to melt, say down into a warmer layer, they'll get a coating of water on them. And remember I told you that hail, ice with a coating of water really bounces back a radar beam? Well, so do snowflakes with a coating of water. They'll really bounce back a radar beam. Now look on the right here, right in here. The radar beam is getting higher and higher and higher, and then it gets in this big layer where it's getting a big reflection, and then it goes away, and now we have just light rain in here. This is a bright band. This is the radar beam traveling through this layer right here with coated snowflakes, with water-coated snowflakes, and they're really reflecting. one thing you can do is if you've got colder air coming in, you can watch this bright band. If it gets closer and closer to the radar, that means you're about to change over to snow, because above this bright band, these are snowflakes. Down in here it's rain, but this is rain-coated snowflakes. And many times I've actually watched that bright band get close to the radar. I walk out the studio just in time to see raindrops mixing with snowflakes, and then it will eventually change over to all snow. So a bright band on radar is basically melting snowflakes. Sometimes you'll see it with hail as well, but I wanted to show you what a bright band on radar looks like. It's just a ring. And you got to remember here, the radar beam is getting higher and higher as it goes away from the radar. So it runs through this layer here, and then eventually it gets above that layer into all snowflakes, and it's showing just snow in here, melted snow, and then rain in here. Pretty cool, huh? So the other cool thing, I've seen this many times on radar. This is a sunset spike. At sunset, the radar is going around, and if it passes right in front of the sun, if the beam is pointed right at the sun at sunset, you'll get energy from the sun 90 million miles away, and it'll pop up a spike on the radar. We see it also at sunrise. And by looking at the direction of that spike, I can tell you right here, for instance, that has got to be probably in June or early July, because that sunset spike is so far north. The sun is setting north. On the equinox, it would set due west, and in the middle of winter, that sunset spike would be down in here. Let me see. Wait, there's a date on here. There you go, June 13th. See, I could tell you that it was summertime because that sunset spike was to the northwest. So yeah, you see sunrise and sunset spikes all the time. This is what a violent tornado looks like on radar. This is a hook echo. We're not even looking at velocity data here. The tornado's right in here, that hole there. Think of a tornado circulating counterclockwise. The wind's going counterclockwise. It's pulling the rain around it and then back in this direction. So that's a hook echo on radar. Now, velocity data would probably also show strong winds toward and away from the radar right next to each other. But before we had Doppler, those are how we saw tornadoes on radar. And unfortunately, it only worked when you had a big tornado close to the radar. Then you could see a hook echo and they'd issue a tornado warning. But tornado warnings just based on hook echoes, well, we missed a lot of them, unfortunately. And there's some other things in here, clear holes and stuff like this. And this is what's called the Puget Sound Convergence Zone, where the mountains funnel the precip, and they see stuff very well on the radar, and big holes on the radar. That happens a lot as well. But I'll just go back here and we'll leave it right here. So that's basically what I want you to know about radar. We will talk more about some of the signatures we see on radar. And we already talked about range folding and velocity folding, and that's the last thing I'll tell you about. I don't have a slide for that, but remember, we have the Doppler dilemma. If we want to see a long ways, we have to send a pulse, slower pulses. But if we want to see high winds, we need to see, in the velocity data, we need to turn the pulse rate up. The pulse repetition frequency needs to be very high. We can then see high winds like in a hurricane, but the problem is we're not tracking the pulses long enough, and we might get a bounce back from a pulse we sent previously and not know where that reflection is coming from. That's range folding. And if we have the pulse rate too low, we get velocity folding where we're not sure what the winds are. That's the Doppler dilemma. If we want to see a long way, we need to see a low pulse rate. If we want to see high winds, we have to have a high pulse rate. The PRF has to be really high, pulse repetition frequency. That's the Doppler dilemma. And we can put up with it now. One thing they do is they'll have the radar, and I'll just go up and show you here real quickly. We'll have the radar do a scan down low with a low PRF, and then it'll do another scan down low at a high PRF, and then it'll go ahead and do the rest of these. That way we get both worlds. We can see high winds and we can get a long distance out. So there are ways to get around the Doppler dilemma, but that's an important thing, and it's something you should understand. I will put that on a test for sure. Low PRF, we can see a long ways. High PRF, we can get high winds, but we can't see as far. So it's a trade-off. All right, that's it. I'll see you in class on Tuesday. Have a good one. Bye.